Hello everyone, I'm Robin Xie from HR Tencent. I'm very glad to introduce this work for you. The title of this paper is Explore, Filter, and Distill Distilled Reinforcement Learning in Recommendation, which focuses on the knowledge distillation between IO-based recommendation models. This research is conducted by the team of WeChat Top Stories. Real-world recommender systems, such as the feed string, usually adopt the list-wise recommendation, which provides a recommended list instead of a single item for each user request. To learn users' personalized preferences, recommendation algorithms should capture informative high-order feature interactions between users and items deriving from median-level user behaviors. Recent years has witnessed the great successes of deep neural networks in recommendation to capture the list-wise rewards. Reinforcement learning-based models are also conducted and verified in real-world systems. However, IO-based recommendation models inevitably suffer from the huge memory and computation costs due to their large-scale models. These memory and computation costs will even multiply when dealing with the list-wise recommendation, since it should recommend a list. Hence, real-world recommender systems should jointly consider effectiveness, efficiency, and expenses, where model compression is a practical solution. Knowledge distillation is one of the most representative and effective models for knowledge transfer and model compression. It eases the training of large-scale neural networks by following a teacher-student paradigm, which transfers the knowledge of large networks into smaller models. The large network is the teacher, and the smaller network is the student. Knowledge distillation not only makes the student smarter and faster for deployment, but also improves the training by further considering additional information in negative logics. For general supervised training in the left, models are learning from positive or negative labels. In recommendation, the labels are impressed clicked or unclicked items, which are sparse. In knowledge distillation, users can learn from both supervised labels and unsupervised instances labeled by the teacher, which also provide essential information. There are some works that have verified knowledge distillation in recommendation. However, there are very few works that conduct KD between IO-based models in recommendation. The main challenges of KD on IO-based recommendation locate in two aspects. First, what lessons should the teacher pass on to the student? Conventional KD in classification tasks could learn additional knowledge from all negative logics of the teacher's softmax layer, which often has less than a few hundred categories. In contrast, it is not possible and also unnecessary to explore all state action in IO-based recommendation, since we have million level item candidates and most of them are irrelevant. An effective KD in IO-based recommendation should explore items that are most likely to be clicked, filter other irrelevant items, and distill the refined knowledge to the student. Second, how much should the student learn from each lesson? The interactions between users and item lists are extremely large. The teacher is not always correct for every action in recommendation. Therefore, the confidence of each lesson should be considered. To solve these two challenges, we propose a novel distilled reinforcement learning framework for recommendation, shortened as DIRAC. The key idea of DIRAC is filter before distillation and distill with confidence. Let's see the right figure. The small circle indicates the labeled item. The big circle represents all possible item candidates. In recommendation, the items are often regarded as implicit negative feedbacks. If we conduct KD with the labeled items, the user-item interactions will be extremely sparse. In contrast, if we conduct KD with all items, the noises of the teacher on unlabeled items and the computational costs are unacceptable. Our model's purpose is to find the gray cloud part, which indicates the informative items for distillation in IO-based recommendation. This figure displays the overall architecture of DRL-RAC, which mainly consists of three modules, including the teacher and student module, the exploring and filtering module, and the confidence-guided distillation module. The teacher and student module contains two value-based IO models, which attempts to predict the scores of recommending certain items in the current states. Without knowledge distillation, the teacher and student are trained separately. The exploring and filtering module focuses on exploring countless user item combinations in the current state and filtering irrelevant user item pairs for the teacher to teach in the following distillation. We design different strategies to decide which unlabeled user item explorations should be taught from both teachers and student aspects. These filtered exploration candidates are used as additional lessons besides real training instances for the following distillation. After filtering, the confidence-guided distillation module conducts both intermediate and output distillations with confidence. We design a listwise KL divergence-based method to distill the Q-value list and conduct a classical hint loss for intermediate distillation. Besides the original IO-based ranking loss, the student can learn from both real training instances and filtered exploration candidates while KD. In online, we only deploy the student network for recommendation to fit the computation and memory requirements. For the teacher network and student network, we directly follow the current state-of-art model. The state contains all user features, contextual information, and previous recommended items features in the list. We use a transformer to model feature interactions and use a listwise GRU to capture the sequential information and get the state embedding. Each action is generating an item in a certain position of the recommended list. For the student, we use DQN for training, along with two knowledge distillation losses learning from the teacher. Conventional knowledge distillation models could benefit from the softmax distributions and the negative knowledge of the teacher as supplies to the hard labels. However, the action in recommendation, that is, recommending an item, may have medium-level candidates. It is extremely time-consuming and not necessary to explore and learn from all negative instances. In physics, scientists usually conduct the filtration process before distillation, which filters all irrelevant impurities that may reduce the distillation efficiency. Inspired by this, we assume that an effective KD should also filter irrelevant actions before the following distillation, focusing on the high-quality user item pairs in teaching. Hence, we propose the exploring and filtering model to find what lessons the teacher should teach the student. Specifically, we first conduct a fast retrieval model to generate 1,000-level unlabeled items as candidates. Second, the teacher and student explore and score these item candidates in the current state separately. Third, the teacher-led and student-led lessons are conducted to select top informative items from two specs. Precisely, the teacher-led lesson selects items with the top K Q values generated by the teacher, while the student-led lesson stacks items with the top K Q values generated by the student. These lessons will generate items that have strong impacts on the final results, which are regarded as informative instances to be distilled. In this confidence-guided distillation model, we designed a confidence-guided list-wise output distillation based on the Cal divergence between the teachers and the students' Q-value lists, and also conduct a confidence-guided hint loss between their intermediate embeddings. The confidence is straightforwardly defined as the bias between the teacher's Q-value and the real Q-value. For unlabeled items, we simply set the average confidence equally for all instances. This confidence is functioned as a decay weight in all distillations backpropagation. We have deployed our DRL rack on a real-world recommendation system in WeChat. Note that there are two types of IL explorations in our model. The offline IL exploration is in the exploring and filtering module supervised by the teacher, while the online IL exploration is learning from online randomness and supervised by real user feedbacks. Both explorations contribute to the final performance. We conduct extensive experiments in both offline dataset and online system. We aim to answer the following four research questions. RQ1. How does DRRAC perform against competitive baselines in offline? RQ2. How does DRRAC perform in online system? RQ3. What are the influence of different components? RQ4. What are the influence of different parameters in DRRAC? For offline evaluation, we build a new dataset from a widely used list-wise system named WeChat Top Stories, which has billion-level instances. In the main experiment, we found DRRAC has better performance with less computation and memory costs compared to the teacher network and other baselines. We also verify the effectiveness of DRRAC in online A/B test. In ablation study, we observed that both the exploring and filtering module and the confidence are effective. Moreover, we also verify the advantages of jointly considering two types of distillation losses as well as the network architecture. Finally, we also find that our model is robust with different compression rates to fit different online demands. That's all my presentation. Thank you for listening.